Hi, this is a really rough first podcast on periodic trends for those of you who are absent, and for those of you who are here and need a review. I like to nickname periodic trends lefty-loosey, righty-tighty. And the reason I do that is because everything that's on the left-hand side of the periodic table is held very loosely, and everything on the right-hand side is held very tightly. And when I talk about being held very tightly, the only thing we really care about in chemistry, unless we're talking about nuclear chemistry, is we're talking about all the valence electrons. And what holds them in place is the nucleus. And so, lefty-loosey, everything on the left-hand side is held very loosely by the nucleus. And on the right-hand side, things are held very tightly. As a matter of fact, I like to think of a Marine Corps haircut, which is called a high and tight. So if you think of high and tight, like a Marine Corps haircut, high and tight to the righter you go, and the higher you go in the periodic table, the nucleus holds the electrons tighter. I just kind of threw this together real fast, so these are your key vocabulary words: electronegativity, ionization energy, electron shielding, atomic radius, ionic radius, and electron affinity. We're going to come back to this later. Okay, as a matter of fact, we're going to come back to this later too. I may or may not get to that this podcast. And so these key vocabulary words 1, 2, 3, and 4 are the nitty-gritty of what's going on in electronegativity and periodic trends. Electronegativity, I like to nickname electronegativity electromagnetivity. That's not completely right, but I tell you what, if you think of an electromagnet, and I had an iron suit on, what would you think of? I think of being pulled really, really strongly by it. And so electronegativity is exactly that. It's the pull of the nucleus on the valence electrons. Okay, if you remember, the valence electrons are the outermost electrons, right? So bad Bohr model over here. Here's some electrons right here, right? 2, 3, 4, 5, 6, 7, 8. 2 here. If I had this right here, this would be sodium. Bad drawing, sorry. But these electrons right here, all these on these energy levels are the inner electrons. Those are called kernel, or the inner electrons. Okay? This one electron right here is called the valence electron. It's the outermost electron. It's the one that's pulled away in bonds. And it's what determines how it acts as an element. So electronegativity, again, is the pull of the nucleus on the valence electrons. Okay? Ionization energy, on the other hand, goes hand in hand with it. It has to do with how much energy, and again, these aren't formal definitions, but they're definitions so that you can understand them. The ionization energy is how much energy it takes, abbreviate energy with the E, for another element to take an electron away. To take an electron away. Okay? So let's flip here for a second, and I kind of, like I said, pull this together real quick. So here's my size, and this is how they determine it. Atomic radius, which is what? Atomic radius is the distance from the inside to the outside, like a radius of a circle. Well, how do they do that? They can't see one, so they take a covalent bond. They take from center to center, right? That's the radius, and they split that in half, and they can figure out just one radius. So that's how they figure out this atomic radius, and atomic radius is exactly that. It's the radius of an atom from the center to the outside. This is how they determine it, just so you have an idea. Okay? And so let's talk about sizes of atoms, and we're going to talk about it in terms of electronegativity, so we're going to come back to this. Okay? So, with this word electronegativity, I'm going to draw a really bad periodic table here. Sorry, this is squeaking on. Okay? So if you think about it, let's draw a bad Bohr model. here we have up top is 1 energy level, and we have 2, and then we have way more. Okay, and on the left, if you notice, we're going to go back to this lefty-loosey. On the left-hand side of the periodic table, notice there's an L there. So on the left-hand side, things are held very loosely, especially down low. Things are looser down low, and things are held very tightly up here. If you remember electronegativity chart, this was fluorine. Fluorine had a value of 4.0, the best darn puller on the periodic table. Remember? And this right here was poor little francium, 0.7. And francium is a lousy holder-oner of its electrons. So, if you agree with me right now, just say that metals lose their electrons. The reason why they lose their electrons is they're lousy holder-oners. They have a lousy pull. A lousy pull of what? The lousy pull of the nucleus on the valence electrons. And so if you talk about that, what's the pull of the nucleus on the valence electrons? That's electronegativity, isn't it? So they have a really bad, a really low electronegativity right here. Okay? And these have a very high electronegativity. We'll talk about why in a minute. Okay? So for right now, you need to know that on this side of the periodic table, right here, there's low electronegativity, and over here there's high electronegativity. So let's talk about what happens as you go down the periodic table. Okay? Let's look at the size of our atom here. And I'm actually going to get rid of this. Okay? Come back to our pen here. And we're going to draw a very bad Bohr model again. Okay, so we're going, oh, that's really thick, sorry. You get the idea. 1, 2, 3. So as I go down, remember what that's called? A family. Oh, that really looks great, doesn't it? Or group. What happens to my radius? My radius gets very, very large. So here you got another L word. On the left-hand side, things are held very loosely. There's a low electronegativity, a very lousy hold on the left-hand side in general. And what happens to that lousy holding onto? If this is my nucleus and there's my electrons, and here's my nucleus and here's my valence electrons, here's my nucleus and my valence electrons, look what's happening. What's happening to the distance between the nucleus and the valence electrons as you go down a family or a group? The distance is increasing. The distance gets larger between the nucleus and the valence electrons, doesn't it? Okay? So if I'm a positive in here, and here's a negative out here, what's true about the hold or the attraction between them? This has got a really good attraction right here, doesn't it? This is a lousier attraction, and this is even lousier. So on the left-hand side, where things are held very loosely, and the electronegativity is very low, which is the pull of the nucleus on the valence electrons, as you go down a family or group, the electronegativity gets even lower. It's got an even lousier pull of the nucleus on the valence electrons, doesn't it? Why? Because the distance between the nucleus and the valence electrons increases, doesn't it? Okay? So the pull gets lousier. It has a lower electronegativity, a lower pull. Okay? Or less of a pull. Right? Now, there's two reasons actually, besides just the distance, right? Distance increases as you go. Distance of what again? Distance between the nucleus and the valence electrons. It increases as you go down, doesn't it? Okay. But what else is happening? If you look right here, I've got more and more energy levels, right? Here there's only one energy level. Here there's, I'm redrawing these by the way, here there's two. Here there's more. And so what's happening is these electrons here on this energy level, and I just erased that, that's good. These electrons on this energy level block the pull of the nucleus on these electrons right here. They're in the way. So in other words, this nucleus is pulling on two electrons right here. This nucleus is pulling on not only on these electrons here, but then it's pulling on this one. So it's busy pulling on these electrons, these interkernel electrons. Look at this nucleus. This nucleus right here is not only pulling on these electrons first, then it's spending its energy pulling these electrons, and by the time it pulls to an electron that's out here, it has a really hard time pulling on it. This is called electron shielding. When I think of a shield, I think of battle, okay, or blocking. So electron shielding, this has lots of electron shielding as you go lower. Okay, so if there's lots of electron shielding as you go lower, what happens to the attraction between the nucleus and that valence electron out here? It gets even lousier. Okay, so if you look at this, oh, this is lovely handwriting. If you look at it, on the left-hand side of the periodic table, let's go back here, sizes of atoms. What happens as you go, and this is from top to bottom here, right? Things are very, look at this, sizes of atoms. This has to do with electronegativity. This right here is what? This vocabulary word is atomic radius. But this, I can spell. This right here has to do with electronegativity. What's electronegativity again? The pull of the nucleus on the valence electrons, or the pull of the protons on the valence electrons, the negatives, right? So if I was to draw this little Bohr model here and this one down here, which has way more energy levels, the distance between the nucleus and the valence electrons increases as you go down, right? So the pull of the protons in the nucleus on the valence electrons here is way worse. It's less of a pull. What else happens as you go down? There's increased shielding. What's shielding? All those inner electrons blocking the pull or shielding the pull of the nucleus on this valence electron out here. Okay? So there's two reasons as you go down why the radius increases and why the electronegativity gets lower. Now let's talk for a second about fluorine. And if you notice, we don't even really talk about these noble gases here. They're full. Their valence electron's full. They don't need to play this game, this bonding game. Okay? And when we talked about bonding, if you noticed, high electronegativity and low electronegativity combine to make something like francium fluoride. Okay? Or sodium chloride. Ionic compounds, a positive and a negative. A big gainer and a big loser. And these are losers. Why? Because they have a low electronegativity. The pull of their nucleus on their valence electrons is lousy. And these are super duper. Matter of fact, remember, fluorine's the best darn polar on the periodic table. So it comes over here and says, yo, francium, give me one of your electrons. And francium says, sure, not a problem. Okay? So let's talk about this for a second. If fluorine had a choice of yanking an electron away from this one and this one, some of this will form and some of this will form, but guess what? Most of this is going to form. Why? Because this has a worse pull of its nucleus on its valence electrons. Its electronegativity is very low because there's lots of shielding. Okay? There's more inner electrons blocking the outer electrons, the valence electrons. And the distance increases. Doesn't the atomic radius get bigger? That's what this is right here. This whole chart is atomic radius. The radius is getting larger, which means the distance between the protons and the electrons is getting larger. It's getting farther away, so it's got less of a pull. So electronegativity is low. Now, this whole stealing thing, fluorine comes along and goes, yo, give me an electron. Guess what happens? That has a fancy name, too. Of course, it has to have one, right? That's called ionization energy. And ionization energy is the amount of energy that fluorine needs to put in to take an electron away from lithium, or that fluorine has to put in to take an electron away from rubidium here in this case. Which one do you suppose fluorine has an easier time with? If you said rubidium, you are completely correct. Why? Well, guess what? It's got a low electronegativity compared to lithium, right? It's got a lousier pull on its valence electrons because there's lots of shielding, and the distance is larger. Therefore, it's way easier for fluorine to take an electron away from it. So if you notice, it has a low ionization energy. These two go hand in hand, don't they? Electronegativity and ionization energy, they go hand in hand. How come? Because if I have a lousy hold of my nucleus on my valence electrons, then it's going to be really easy, or not a lot of energy is going to have to go in to take an electron away. Okay? So let's go back here for a second. Okay, we've talked about electronegativity, pull the nucleus on the valence electrons. We've talked about ionization energy, which is the amount of energy it takes for another element to take an electron away from me. And if I have a lousy pull, I've got a low electronegativity. If I've got a lousy pull, then it takes a very low amount of energy to take an electron away from me. And chances are that's because I have a large atomic radius and because I have lots of electron shielding. Those are things that contribute to the fact that these two are low. And if you notice, they go hand in hand, don't they? Okay? Remember, we're not going to do these right now. Okay? All right, so let's come over here. And let's clear this. All right? And bad periodic table again, sorry. But just so you get the idea. Okay. Where was my electronegativity low again? Low over here. That was very righty-tighty. High and tight to the right. High over here, electronegativity. Low electronegativity. This is also low ionization energy. Amount of energy to take an electron away. Okay. This is high ionization energy. Amount of energy to take an electron away from here. Good luck. Fluorine's the best darn puller on the periodic table. Good luck taking an electron away from it. Okay, so size of the atom again, atomic radius. It's large over here, right? It gets even larger as you go down. Two reasons. You're adding on more energy levels, right? Packing it on. And also what's happening? Lots and lots of shielding as you go down, right? Okay, so larger atomic radius, lots of shielding. So if you compare on this side, it takes way less energy to take an electron away from this atom down here than it does up here, right? Okay. So that makes sense, hopefully. Okay, I know this is fast, but you can always replay it. So if you go across now, what's going to happen? We said what? Righty-tighty, lefty-loosey, or lefty-loosey, right? Loose over here, very large over here. So that means things are very small over here. All right? So I'm going to exaggerate, but I'm going to go ahead and draw what would happen here if I went across. All right? So let's just pick one. I'll pick lithium, for example, which has 3 protons and 3 electrons. And if you look, if you go across a period, it's almost like you're doing this. It's like you're adding more and more electrons to this energy level. Bad Bohr model, but bear with me. Okay? If you notice, that distance between those really isn't changing that much, is it? Okay? So I'm not adding another energy level, am I? I'm adding to the same energy level. So, not quite, but this is what it's like. Okay? Picture this. If I'm adding another proton, 4 protons, 4 electrons, 5 protons, 5 electrons, as I go across a period, right? Write a sentence across a piece of paper, put a period at the end, so periods go this way. So what's happening if I'm not adding any more energy levels is that the pulling power, the effective nuclear charge, the pulling power of my nucleus right here on those electrons is getting a lot stronger. So there's a harder pull of my nucleus on my valence electrons as I go across. And so what actually starts to happen is my radius goes from large on this side to a little smaller, to a little smaller, to a little smaller. Okay? Now, we're going to learn a couple classes from now that this isn't completely the way it goes across. There are some exceptions, but for right now, the trend is you go from top to bottom on this side. If this was up here, it would be very large down here. See that? Okay? As you go across, it goes from large over here to smaller, because the distance between the nucleus and the valence electrons isn't changing. There's no shielding. You're getting out the same energy level. right? Same energy level. So the pull of those protons gets harder. So this is smaller over here, atom. Now what happens over here? What am I doing as I go over here? I'm adding what? Energy level after energy level. So it's getting larger as you go down too, isn't it? So it gets larger as you go down on this side. But if you compared this element right here to this element right here, this side is still larger. Because as you go across, what happens? The pull of the nucleus on the valence electrons gets stronger because there's no shielding. Look, you're adding on the same energy level. Okay? So this is atomic radius versus atomic number. This is a little tricky because you got to look at a periodic table, but here's atomic number. I'm adding more and more protons. All right? This is going across a period. Okay, it gets a little smaller, not much. Then what happens? I get larger because now I've gone and Bohr model the atom from here to here. I've added a whole other energy level. Now look what happens to my atomic radius as I'm going across a period. I'm going in this direction on the periodic table. It gets smaller, doesn't it? Okay? Not as tiny as you might think, but it gets relatively smaller until you get to that noble gas and its electron, the energy level is full. Right? Now look at the atomic radius here. How come this right here is larger than lithium? Well, guess what? It has a whole other energy level. So it's got a larger atomic radius. Alright, and that's why K is even larger. It's further down. So this is going down a group. See that right there? There's my first one, there's my second one, there's my third energy level, there's my fourth energy level. So look what's happening to my radius. You tell me what's happening to my electronegativity. My electronegativity is getting lower, isn't it? It's easier to take an electron away. Why? What was it again? The protons in the middle have a harder time holding on to this outer electron here. Look at this outer electron. This proton has these protons has a really hard time holding on to those. And what about this right here? Not only is the distance getting bigger, but look at all these energy levels that are blocking, right? Okay? So as the atomic radius gets larger, and if you're looking at a periodic table, you would be moving this way on a periodic table. The distance between the nucleus and the valence electrons increases, and there's lots of shielding. Okay, so here's ionization energy versus atomic number. Look at these. Here's my atomic radius, right? Very large atomic radius, super large, even larger atomic radius. That's going down a family, right? Look what happens to my ionization energy. It gets low, lower, and even lower. Not as much as you think, but look at that. It's lower, isn't it? Okay? It's easier to take an electron away from potassium than it is to take an electron away from lithium or even from hydrogen. How come? Because the radius for potassium is larger. Lots of shielding. Distance between the nucleus is very large. So now let's think about this. Ionization energy, what's that really have to do with? It has to do with electronegativity. So guess what? This has got a low electronegativity. This is even lower. This is the lowest of these four, isn't it? Right? How come? Because it is larger. The pull of its nucleus on its valence electrons is lousy. So ionization energy, electronegativity go hand in hand. They're the same. Okay. I'm not sure if I want to go into this right now. Sorry. Oh, here's a good picture of what's happening as we go across the periodic table. This is effective nuclear charge. So if you're lithium and you have 3 protons and 3 electrons, see that right there? Beryllium has 4 protons and 4 electrons. This one has 5 and 5. Look what happens to the radius. These protons in here are pulling super hard on this. And so the size goes from large to small to smaller as you go across a period. Okay? So that's kind of what we talked about in class as far as electronegativity and ionization energy. You need to be sure that you know those trends really well. I have a worksheet for you to look at. Okay? So one more time as a wrap up, just in case you need it. Electronegativity and ionization energy are both low as you go lower over here. They're low over here anyway, and they're really high over here. High ionization energy, high electronegativity. You need to make sure you're comfortable with what those vocabulary words are. Okay? The atomic radius, E-neg, and this is ionization energy. Right? It's low over here. Gets very, very high as you go across. Pull gets really strong. As you go lower, the atomic radius gets larger. Okay, therefore the distance increases between the valence electrons and the nucleus, and there's also increased shielding or blocking of those inner electrons, blocking the pull in the nucleus on the outer electrons. As you go across, it gets smaller again, but these are a little larger. They're still high, but they're, not larger. These are a little lower than these up here, okay? But these are still, over here on this side, are still higher than the values over here, okay? Because as you go across, the pull of the nucleus on those valence electrons doesn't change, the distance doesn't change, and so the pull gets stronger by those protons in the nucleus. I think we covered it. Atomic radius, electronegativity, ionization energy. And I think it's a wrap. I'll redo this so it's better, but at least you get an idea. Okay? Come see me for the worksheet, and you have some problems to do.